Welcome! Today, we'll be tackling LeetCode problem number 662, maximum width of binary tree. In this problem, we aim to determine the maximum width of a binary tree, considering the number of nodes between the leftmost and rightmost non-null nodes at each level. Let's dive into the details and explore the solution approaches. In this problem, we're tasked with finding the maximum width of a binary tree. The width of a binary tree at any level is defined as the number of nodes between the leftmost and rightmost non-null nodes, including any null nodes in between. Our goal is to determine the largest width among all levels of the tree. The input to the problem is the root of a binary tree, where each node holds an integer value. The output is a single integer representing the maximum width of the tree. It's worth noting that the result will always be within the range of 32-bit signed integers, which means it won't exceed 2 to the power of 31. This provides a guarantee that we won't encounter overflow issues while solving the problem. Let's look at the first example to better understand the problem. The input binary tree is represented as an array 1, 3, 2, 5, 3, null, 9. Visually, the tree is structured like this. The root node is 1, with children 3 and 2. Node 3 has children 5 and 3, while node 2 has only one child, 9, on the right. The output for this example is 4. Here's why. At level 0, the width is 1 because there's only the root node. At level 1, the width is 2, as there are two nodes, 3 and 2. At level 2, the width is 4 because, when you count from the leftmost node to the rightmost node, you include 5, 3, a null node, and 9. The maximum width across all levels is 4, which is our answer. Now, consider the second example where the input tree is 1, 3, 2, 5, null, null, 9, 6, null, null, 7. The tree is visualized as follows. The root is 1, with children 3 and 2. Node 3 has a single left child, 5, while node 2 has a right child, 9. Additionally, node 5 has a left child, 6, and node 9 has a right child, 7. The output here is 7. Let's break it down. At level 0, the width is 1 because we have only the root node. At level 1, the width is 2 due to nodes 3 and 2. At level 2, we count 6, followed by 5 null nodes, and then 7, resulting in a width of 7. This is the widest level of the tree, making 7 our result. For the third example, the input tree is 1, 3, 2, 5. When visualized, the tree has a root node 1, with 3 and 2 as its children, and node 3 having a single left child, 5. The output in this case is 2. Here's why. At level 0, the width is 1 because there's just the root node. At level 1, the width is 2, as there are two nodes, 3 and 2. At level 2, the width is 1 because there is only one node, 5, and no other nodes at this level. Therefore, the maximum width of the tree is 2. Finally, let's consider some constraints and edge cases. The tree can have up to 3,000 nodes, so our solution must handle large inputs efficiently. Node values range between 0 and 10,000. In terms of edge cases, a single node tree will always have a maximum width of 1. For trees where all nodes are skewed to one side, the width at every level will also be 1. Additionally, trees with null nodes between non-null nodes must include those null nodes in the width calculation. Keeping these points in mind will help us design a robust solution to the problem. To solve the problem of finding the maximum width of a binary tree, we need to focus on calculating the width at each level of the tree. The width is the count of nodes between the leftmost and rightmost non-null nodes, inclusive. One potential approach is the brute force approach, which involves performing a level-order traversal using breadth-first search, or BFS. Here, we explore all nodes level by level. To calculate the width, we keep track of the positions of the leftmost and rightmost nodes at each level. By maintaining a queue that stores both the nodes and their positions, we can extract the nodes at each level, compute the width using the positional indices, and then update the maximum width observed so far. This method is efficient with a time complexity of O(n), where n is the number of nodes in the tree, since each node is processed exactly once. The space complexity is O(w), where w is the maximum width of the tree, because the queue will contain all nodes at the widest level. However, one limitation to note is that this approach requires careful handling of null nodes and their positions to ensure accurate calculations. Another approach to solving this problem is using recursive depth-first search, or DFS, combined with positional indexing. In this method, we traverse the tree recursively and keep track of the position of each node relative to its parent. By using a dictionary to store the leftmost position of each level, we can dynamically calculate the width by comparing the current node's position with the recorded leftmost position for that level. The recursive traversal involves passing both the current level and position to the function, and for each new level encountered, we update the leftmost position if it hasn't already been set. The time complexity remains O(n), as each node is visited exactly once, and the space complexity is O(h), where h is the height of the tree, due to the recursion stack. However, one limitation is that this approach relies on recursion, which can lead to stack overflow if the tree is very deep, making it less robust for highly unbalanced or skewed trees. The strategy we ultimately chose for this problem is the brute force approach using BFS with a queue. This method aligns well with the problem's requirement to process nodes level by level. By maintaining positional indices for each node, we can calculate the width of each level efficiently. A key advantage of BFS is its intuitive handling of node positions. The positions of child nodes can be derived directly from their parent's position using simple formulas: left child equals 2 times the parent's position, and right child equals 2 times the parent's position plus 1. This ensures accurate width calculations, even in the presence of null nodes. While BFS does require slightly more space compared to DFS due to the queue size, it avoids the risk of stack overflow, which can occur with deeply skewed trees when using recursion. Additionally, BFS is easier to debug and maintain, making it a more robust and practical choice. By leveraging positional indexing, the BFS approach strikes a good balance between simplicity, efficiency, and reliability, allowing us to determine the maximum width of the binary tree with confidence. To start, let's understand the problem. We want to find the maximum width of a binary tree. The width of any level is defined as the number of nodes between the leftmost and rightmost non-null nodes at that level, inclusive. Our task is to calculate this width for every level and return the largest one. To solve this, we use a breadth-first search, or BFS, approach combined with indexing. By assigning a position index to each node as we traverse the tree level by level, we can calculate the width of each level efficiently. The process begins by initializing a queue for BFS traversal. This queue will store pairs of nodes and their indices, where the root node starts with an index of 0. This setup ensures that we can track the positions of nodes relative to each other as we move through the tree. Now, we proceed by processing the tree level by level. For each level, we determine the positions of the leftmost and rightmost nodes using their indices. These are stored as level_min and level_max. The width of the level is simply the difference between these two indices, plus 1. Next, for every node at the current level, we add its children to the queue with their respective indices. The left child gets an index of 2*parent_index, while the right child gets 2*parent_index plus 1. This indexing scheme maintains the relative positions of nodes within the tree, even if some nodes are missing. After calculating the width of the level, we update the maximum width encountered so far. Once all levels have been processed, the maximum width is returned as the result. This approach relies on a few key insights. By assigning indices to nodes, we can calculate the width of each level without needing to explicitly construct the full tree structure. The indices ensure that we account for any gaps between nodes. Using BFS guarantees that nodes are processed level by level, which is essential for width calculation. Consider the edge cases. In a tree with only one node, the width is simply 1. For skewed trees, where nodes are aligned to one side, the width remains 1 at all levels because there is only one node per level. Additionally, null nodes between non-null nodes do not affect the width calculation because we focus on the indices of the leftmost and rightmost non-null nodes. To implement this, we use a queue to manage the BFS traversal, and variables like max_width, level_min, and level_max to track the necessary information during the process. Here, we have the Python implementation of the algorithm. After initializing the queue with the root node and an index of 0, we set max_width to 0. The core of the algorithm lies in the while loop, which runs as long as there are nodes in the queue. At each iteration, we determine the size of the current level and retrieve the indices of the leftmost and rightmost nodes from the queue. This allows us to calculate the width of the level and update the maximum width if necessary. Then, we process all nodes at the current level, dequeuing each node and adding its children to the queue with their respective indices. The left child is assigned 2 index, and the right child 2 index plus 1. Once the loop completes, the function returns the maximum width recorded. This implementation ensures that every node is processed exactly once, and the relative positions of nodes are preserved. Finally, let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the number of nodes in the tree, since each node is visited exactly once during the BFS traversal. The space complexity is O(w), where w is the maximum width of the tree. This is because the queue stores all the nodes at the current level, and the size of the queue is at most the width of the widest level. This implementation is optimized by using indexing to avoid extra data structures for tracking node positions. Additionally, leveraging a deque ensures efficient operations for adding and removing nodes during traversal. Overall, this approach provides an efficient and elegant solution to the problem of finding the maximum width of a binary tree. This code calculates the maximum width of a binary tree using a level order traversal (BFS) approach. Let's break it down step by step. 1. Imports and initialization. The solution uses a deque from the collections module to implement the queue for BFS. A max_width variable is initialized to store the maximum width of the tree. 2. Edge case. If the input root is null, the function immediately returns 0, as the tree has no width. 3. BFS setup. The queue starts with the root node and its index, 0. The index represents the position of the node in a hypothetical complete binary tree. 4. Level processing loop. The outer while loop iterates as long as there are nodes in the queue. For each level, the level_length captures the number of nodes at the current level. The first _index and last _index are extracted from the indices of the leftmost and rightmost nodes in the queue. The width of the current level is calculated as last_index, first_index plus 1, and used to update max_width. 5. Node expansion. For each node in the current level, the node is dequeued, and its left and right children, if they exist, are enqueued with updated indices. The left child's index is 2 index. The right child's index is 2 index plus 1. 6. Result. After processing all levels, the function returns the max_width. This approach ensures that we compute the width using indices that simulate positions in a complete binary tree, even if the tree is sparse. The time complexity is O(n), where n is the number of nodes in the tree, as each node is processed exactly once. The space complexity is O(w), where w is the maximum width of the tree, due to the queue storage. To tackle the problem of finding the maximum width of a binary tree, we start by defining our tree node structure and implementing the core logic within the solution class. The method width of binary tree takes the root node of the tree as input. If the root is null, we return 0 immediately, as there's no width to calculate. Next, we define a variable max width to keep track of the maximum width encountered so far. To traverse the tree level by level, we use a queue that stores pairs of nodes and their respective indices. These indices represent the node's position in a virtual binary tree structure. We initialize the queue by adding the root node with an index of 0 and then enter a while loop that processes each level of the tree as long as the queue is not empty. Within the while loop, we start by determining the size of the current level using the queue's size. We also retrieve the index of the leftmost node at this level, which helps in calculating the width later. For now, we initialize the last index variable to the same value as first index. Then, we iterate through all nodes at the current level using a for loop. During each iteration, we dequeue a pair to get the current node and its index. The last index is updated to the current node's index, ensuring it always represents the rightmost node's position at this level. If the current node has a left child, we enqueue it with an index of 2 index, while the right child, if present, is enqueued with an index of 2 index plus 1. After processing all nodes at this level, we calculate the width as last index, first index plus 1 and update max width to the maximum of its current value and the width of this level. This ensures we always retain the largest width encountered so far. Finally, we return the max width as the result once all levels have been processed. Additionally, since the JavaFX pair class might not be available in every environment, we define a helper pair class within our solution. This class is generic and takes two type parameters, k and v, representing the key and value of the pair. The constructor initializes these fields, and there are getter methods getKey and getValue to retrieve the respective values. This helper class makes it easy to store and manipulate node index pairs while traversing the tree. With this implementation, the solution efficiently calculates the maximum width of the binary tree in a level order traversal approach. Here, we have a simple binary tree. Our goal is to calculate the maximum width of this tree. To do this, we start by initializing two variables, max_width, which keeps track of the maximum width encountered so far, and q, which is a decinitialized with the root node and its index, starting at 0. At the first level, there is only one node, so the level_length is 1. The first underscore index and last underscore index are both 0. Using the formula for width, max_width becomes 1. Now, we process node 1. Its left child, node 3, is added to the queue with index 0, and its right child, node 2, is added with index 1. At this point, the queue contains these two nodes for the next level. Moving to the second level, the level_length is now 2, with first underscore index at 0 and last underscore index at 1. The width at the second level is calculated as 2, which updates max_width to 2. Processing begins with node 3, which has a left child, node 5. Node 5 is added to the queue with index 0. Node 3 doesn't have a right child, so nothing else is added for it. Next, node 2 is processed. Since it has no children, nothing is added to the queue for this node. At the end of this level, the queue contains only node 5 for the third level. For the third level, the level_length is 1, with first underscore index and last underscore index both at 0. The width remains 2, so max_width is unchanged. Node 5 is processed, but since it has no children, the queue becomes empty. With no more nodes to process, we conclude that the maximum width of this binary tree is 2. Now, let's look at a full binary tree example. We start with the root node, initializing max_width to 0 and the queue with the root node at index 0. At the first level, there is only one node, so level_length is 1, and first underscore index and last underscore index are both 0. The width of this level is 1, which updates max_width to 1. Processing node 1, we add its left child, node 3, with index 0, and its right child, node 2, with index 1, to the queue. At the second level, the level_length is 2, with first underscore index at 0 and last underscore index at 1. The width of this level is 2, so max_width is updated to 2. Processing node 3, we add its left child, node 5, with index 0, and its right child, node 3, with index 1. Then, processing node 2, we add its left child, node 9, with index 2, and its right child, node 7, with index 3. The queue now contains these 4 nodes for the third level. At the third level, the level_length is 4, with first underscore index at 0 and last underscore index at 3. The width of this level is 4, which updates max_width to 4. Processing all nodes at this level 5, 3, 9, and 7 reveals that none of them have children, so no nodes are added to the queue. With the queue now empty, we finish processing this tree and determine that the maximum width is 4. This example demonstrates how the algorithm handles a balanced, full binary tree, where the maximum width occurs at the deepest level. Finally, let's examine a sparse binary tree. Starting with the root node, we initialize max_width to 0 and the queue with the root node at index 0. At the first level, there is only one node, so level_length is 1, and first underscore index and last underscore index are both 0. The width of this level is 1, which updates max_width to 1. Processing node 1, we add its left child, node 3, with index 0, and its right child, node 2, with index 1, to the queue. At the second level, the level_length is 2, with first underscore index at 0 and last underscore index at 1. The width of this level is 2, so max_width is updated to 2. processing node 3, we add its right child, node 8, with index 1. Then, processing node 2, we add its right child, node 4, with index 3. The queue now contains nodes 8 and 4 for the third level. At this level, the level underscore length is 2, with first underscore index at 1 and last underscore index at 3. The width is calculated as 3, which updates max underscore width to 3. Processing nodes 8 and 4 reveals no children to add, leaving the queue empty. The maximum width of this sparse binary tree is therefore 3. To analyze the time complexity of the algorithm, let's break it into its key components. First, the algorithm performs a level-order traversal of the binary tree using breadth-first search, or BFS. This means that each node in the tree is visited exactly once, and any child nodes are processed as part of this traversal. This step contributes O(n), where n is the total number of nodes in the tree. Additionally, for each node, we calculate its positional index using simple arithmetic operations like multiplying or adding constants. These calculations are performed in constant time, O(1), for each node. Since there are n nodes, this step also contributes O(n) in total. Combining these, the overall time complexity of the algorithm is O(n). Now, let's examine the space complexity. The primary factor here is the memory required for the BFS queue, which holds tuples containing each node along with its positional index. The queue size is determined by the maximum number of nodes at any level of the tree, which we refer to as m, the maximum width of the tree. In the worst case, the queue will contain all the nodes at a single level, making its size proportional to m. Additionally, the positional indices stored as part of these tuples are simple integers, so their contribution to memory usage is negligible compared to the nodes themselves. Therefore, the overall space complexity of the algorithm is O(m), where m is the maximum width of the binary tree. To understand the algorithm's performance across different scenarios, we can consider the best, average, and worst cases. In the best case, the tree resembles a linked list, meaning it is highly unbalanced and has a maximum width of 1. Here, the space complexity is O(1), while the time complexity remains O(n), since every node is still visited. In the average case, for a balanced binary tree, the width of the tree grows exponentially with its height. For example, in a perfect binary tree of height h, the maximum width is 2(h1). Even in this scenario, the time complexity remains O(n), and the space complexity corresponds to the maximum width, which simplifies to O(n). For the worst case, in a complete binary tree, the maximum width occurs at the last level, which can be roughly n/2 for n nodes. This results in a space complexity of O(n). When comparing to a naive approach, which involves manually counting nodes at each level, the given BFS-based solution is significantly more efficient, as it avoids repeated level traversal and achieves O(n) time complexity. The big O notation for the algorithm can be formally justified as follows. For time complexity, the BFS traversal processes each node in the binary tree exactly once. Since there are n nodes, and each node is processed in constant time O(1), the total time complexity is O(n). For space complexity, the limiting factor is the BFS queue, which stores all nodes at a single level during traversal. In the worst-case scenario, this corresponds to the maximum width of the tree, m. Hence, the space complexity is O(m). This analysis demonstrates that the algorithm is optimal for solving the problem, providing the best achievable time and space complexities for this task. When solving the maximum width of binary tree problem, there are a few common mistakes to watch out for. First, one of the biggest pitfalls is not accounting for null nodes when calculating the width. The width of a level is defined as the span between the leftmost and rightmost non-null nodes, and this span can include null nodes in between. If you only count the non-null nodes, you'll get an inaccurate result. Another common mistake is using the wrong data structure for level traversal. For example, if you use a simple queue without tracking positional indices, you won't have the necessary information to compute the width of each level. Positional indices are crucial because they allow you to measure the distance between the leftmost and rightmost nodes. Finally, there's the issue of integer overflow in large trees. When using unbounded integers to represent the positions of nodes, the indices can grow exponentially in deep trees, potentially leading to overflow. To avoid this, you can normalize the indices by subtracting the leftmost index at each level, which keeps the values manageable and avoids this problem. Another mistake to avoid is relying on inefficient traversal approaches. While depth-first search, or DFS, can technically solve the problem, it requires meticulous bookkeeping to track the leftmost and rightmost indices at each depth. Without this careful management, errors can easily arise. Breadth-first search, or BFS, is generally a simpler and less error-prone approach because it naturally processes nodes level by level and allows for straightforward tracking of indices. Additionally, some may confuse the concept of width with depth. Depth refers to the number of levels in a tree, whereas width is the span of nodes at each level. Mixing up these two concepts can lead to faulty logic, so it's important to keep them distinct while working through the problem. From an interview perspective, this problem highlights several key patterns. It combines tree traversal concepts with positional tracking, which are recurring themes in binary tree problems. BFS is often the preferred method for level-order traversal scenarios, while DFS can also work if you carefully manage the positional indices. A good practice is to normalize indices at each level by subtracting the leftmost index so you can avoid overflow issues and simplify the calculations. In terms of complexity, you're generally expected to achieve a time complexity of O(n), where n is the total number of nodes in the tree, because each node is processed exactly once. The space complexity is O(w), where w is the maximum width of the tree, representing the size of the queue at its largest. Be prepared to handle edge cases as well, such as sparse trees with large gaps, single-node trees, completely unbalanced trees, or deep trees that could lead to overflow problems. This problem also connects to several related problems that are worth exploring. For example, LeetCode 102, binary tree level order traversal, involves a similar level order traversal concept, making it a great practice problem. Naturally, this problem itself, LeetCode 662, specifically focuses on calculating the maximum width of the binary tree. Another related problem is LeetCode 104, maximum depth of binary tree, which shifts the focus to determining the depth of a tree rather than its width. Finally, LeetCode 199, binary tree right-side view, presents another BFS challenge that requires tracking nodes at each level, giving you more practice with similar traversal techniques. There are also alternative approaches to solving this problem, each with its own pros and cons. Breadth-first search, or BFS, involves using a queue to traverse the tree level by level while tracking positional indices. This approach is relatively simple to implement and provides a clear mapping of indices, but it does require more memory to maintain the queue. Depth-first search, or DFS, takes a recursive approach, where you maintain a map of the leftmost and rightmost indices at each depth. This can be more memory efficient compared to BFS, but it's also more prone to bookkeeping errors and can be harder to debug. Lastly, a hybrid approach that combines BFS or DFS with index normalization can be very effective. Normalizing indices at each level prevents overflow and ensures robustness even for large or deep trees. While this method adds some complexity to the implementation, it's a great choice for handling edge cases and maintaining accuracy. Great work! To recap, we explored the maximum width of binary tree problem and applied a level order traversal with position tracking to find the solution. Remember, mastering traversal techniques and understanding edge cases will help in many binary tree-related problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!